Hi, I'm here today with Fran, and we get a lot of questions from time to time about powdered metal and things about powdered metal that customers are dealing with. And so we thought it would be a good idea to set this program up where every Friday we put something out on LinkedIn and just kind of talk a little bit with Fran about certain topics concerning the powdered metal and powder metal industry, and to see what he has to say to try to help you provide another resource for you to be able to solve the problems that you're trying to deal with. So Fran, we hear a lot about the history of powdered metal. When did it start and what brought us to where we are today? Could you speak a little bit to that topic?
Sure. Actually, what in the PM business, I mean, the very early PM was done by Chrysler Amplex back in the late 30s with self-lubricating bearings. But that was kind of limited in a sense. But more recently, we like to think of the start of modern PM dating in the early 50s. And, a good example is taking a look at the automotive industry. Automotive is still a key player within the business cycle.
Sure. I think about 80% of powdered metal today goes to the automotive industry.
Exactly. But if you think about it, it's like, was it always this high? And a good example is to look at a 1953 Corvette, which was...
Was that your first car, Fran?
Almost. Ben Franklin and I were on a first name basis, but in the 53 Corvette, which was a rather six-cylinder, rather anemic performing car in its time, it had effectively 1 pound of PM parts, and mainly in the form of some self-lubricating bearings and some shock absorber components. Well, now if you suddenly fast forward, almost 70 years, here it is 2020, and if you look at the brand new CA Corvette, well, it has about 50 pounds of PM parts, if not more. And if you compare the performance of that 53 Corvette to a modern, there is no real comparison. The modern Corvette is actually quite a high performance vehicle, and it relies on PM for a lot of its critical components. So it speaks not only to the growth of PM, but to what PM has been able to do from a performance and a properties perspective to get to this new level of performance to make it suitable in this high performance vehicle.
That's a good point. You talk about, how the performance of the Corvette has changed over those 70 years. How would you characterize powdered metal in that, from a performance standpoint?
Good. And again, if you go back into that 50s time frame, what you primarily had were either sponge-based powders, which was a solid-state reduced material, or some of the powders that were gotten from mill scale. When they were limited in what they could do from a performance/density perspective. I always kind of joke and say, in PM performance, the 3 performance keys of PM are density, density, density. It's a lot like selling real estate. Well, in PM, we're selling real estate. And so it's density, density, density. As the industry evolved and new technologies for making powder came onto stream, the one thing that we were able to do was to improve the whole density criteria. So whereas some of the early parts were in an iron base, maybe 5.0 density was considered high.
Wow.
Now some of the parts that I know we're making here at Horizon, they are 7.4 type densities with single press, single center. So if you look at how that has, the density increments that have taken place almost track hand in hand with how the performance has changed. I remember starting in the industry in the early 70s, and at the time, there were 13 pounds of parts in a car. And I'll always remember talking to a gentleman, and he says, I don't know how we're ever going to get above 13 pounds of powder parts in a car. Well, here we are, almost 50 years later, and we've, almost quadrupled that number. And I think that's really exciting. And I think it opens the door for what I think can go on in the future simultaneously.
So you talk about this growth within there. Where do you normally see those components within a car? I mean, is it one specific area or throughout the car?
It is throughout the car as a general statement, but primarily it's in the drivetrain, the engine, transmissions. Those original shock absorber parts, please don't misunderstand. They're still there, and they're still a very viable component within PM. But if you look at some of the modern cars with connecting rods, main bearing caps, things of that sort, and in transmissions, some of the modern transmissions may have as much as 20 to 25 pounds of parts in a modern transmission. So it's quite a testament to what PM has been able to accomplish. And it's through the innovation of the industry and the people working in the industry that has got us to this level.
So clearly, as we've been able to improve, as you mentioned, the density of the parts, the strength of the parts, the properties, we've been able to apply those parts now into different areas of the automobile, different applications, so to speak.
Yeah, and again, I mean, it's, PM is, as we say, density, 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 but the other part of it is cost. And I mean, PM certainly represents a very cost-effective technique for making these components. And in many cases now they are the preferred choice for new engineers as they look at some of these components is, let's first look at PM to see what it can do for us, and then let's design the part accordingly. So it's been a challenge. It's been a lot of fun, actually.
Yeah.
I mean, when you think about it, some of these parts are, they make millions of them daily. Yeah. It's like losing a golf ball. Don't worry about it. We'll make more tomorrow. But it's the same kind of analogy that they make a lot of these parts, and the car industry really relies on it. And we don't know what would happen to the car industry if something would happen to the PM industry.
So you bring up an interesting point, though. Have we reached the limits of powdered metal? Have we reached, how far can it go? Have we? I would assume at some point you hit the ceiling as far as how strong can you make the part, or.
But again, I think in terms of how far can you go, it depends on your perspective. I'd like to think that no, we haven't reached the limit. The one thing that really hasn't changed in PM is the basic sintering practice. People are still sintering now, in essence, the same way they did 50 plus years ago. If you can change part of that equation, change that game, maybe sinter differently, sinter at higher temperatures, sinter with new and unique material combinations, you might in fact be able to overcome some of these current limitations that we're faced with and move into some of these newer, higher strength areas. And I think that's certainly a very fruitful area for research and opportunities for future development.
In fact, I know we've done a lot of work in that area at higher and higher temperatures, and as you said, opening us up to new elements that we're able to add to the materials and further improve the parts.
Yeah, and it was a great segue for you and I in that regard, but I really think that that's exciting. I mean, if you think about, here we are with 21st century materials and 20th century sintering practices. What happens if you start applying 21st century sintering practices to 21st century materials?
Yeah.
Where can you get it? And you talked about some of the material processes that we worked on. Well, perhaps not to blow our horn too much, but quite honestly, in working in the industry for close to 50 years, we've never seen those levels of performances in conventional press and sinter type components. You would have to go to a forging grade material, and even then you weren't achieving some of these performance criteria. So it really, you asked the question is, have we reached the limit? I'd like to think not. And I mean, not just from a structural standpoint, but what about, the one thing that the automobile is facing right now is electrification.
That's where I was going next. We see today, we've talked a lot about the mechanical aspect of powdered metal.
Yes.
And the applications, the engine, the transmission.
Yes.
But we all know that those things are changing dramatically.
Yes.
As we sit here today, they're changing dramatically. And so what becomes in the future for powdered metal in that world, especially in the automotive industry, perhaps?
And a good thing to look at there is look at how engine technology has changed. If you wanted high performance, you bought a V8. Now you can have a V6 or you can have a 4-cylinder that produces more horsepower than V8s did 10 or 15 years ago. So what happens, though, we talked about connecting rods and bearing caps and things of that sort. Well, suddenly they're going away, or a percentage of them is going away, and that represents a potential limitation for the industry, hindering the growth. We're also looking at, how do electrics fit into that equation? And if you look all over the place, every time you open the newspaper or you turn on the news, you see, who's coming out with the new electric vehicle or a new electric truck? And I think that then, if we don't pay attention to that segment of the market, I think we are going to be remiss as an industry, because that's going to represent a new opportunity, and we need to be attentive to that. And I think unless we do, then we are going to be in trouble again.
Yes. Well, I think it's interesting, and I think, again, you bring up a very good point, because certainly that's an area within Horizon that we've paid a lot of attention to.
Yes.
And we've focused a lot of our resources in the development of these grades of material, magnetic grades of material, whether they're sintered soft magnetics or soft magnetic composites. And maybe we want to talk a little bit about that. What are the differences then? We talk about sintered soft magnetics or soft magnetic composites. What's the difference between all of that?
Interesting question. And I think the thing is, what we're looking at in that case is, with sintered soft magnetics, you're looking primarily DC. And, all right, what do we mean by DC? Well, a car runs off a 12-volt DC battery, okay? So a DC current. And PM fits beautifully in that application. You and I are probably old enough to remember the initial General Motors starter motor that they put in,
right,
which was a DC application. It spurred a lot of interest in the whole magnetics arena for powder metal. But the industry got wise. They said, well, if it fits there, what other kind of things can we do? So the DC, think of it as simply, what can we do with a car or DC battery-driven type devices? So that's a perfect opportunity for sintered soft magnetic materials. And, as a company, what we're looking at, we have pure iron in our toolbox. We have iron phosphorus in our toolbox. We have iron silicon in our toolbox. Now you couple these materials with what we're doing in the advances in our sintering. Wow, that really opens up avenues.
So the topics you talked about earlier on the structural type of components, again, same story, where we're looking at higher and higher temperatures to take advantage of new elements there. Here again, it's the exact same thing works in the sintered soft magnetics. If higher and higher temperatures opens us up to elements that we haven't been able to use in the past.
Exactly, and I think iron silicon has always been sitting out there, and it always required what we would consider higher temperature sintering. But we've gone higher temperature sintering one better with our what we consider our ultra high temperature sintering. So now it not only do you get better performance, and now to be a bit of a geek, I'm sorry, but you also get an opportunity to get some grain growth within those materials. And now larger grains, even better performance. You also get more density because of the sintering process. So I think this opens that door. And the other thing that the auto industry has always been concerned about is weight. If we can give you the same performance with less weight, they love it. The comment used to be, for every pound saved, it's worth $20 to the car companies, because of fuel consumption and some of the CAFE numbers that they fight with on an ongoing basis. So I think, these are the things we're offering, not only magnetically, but also on the structural side. Can we offer you a same component with the same performance, but with maybe some less weight as well? I know I digress. We also wanted to talk about, some of the soft magnetic composites and how they differ. This is where it gets a little esoteric at times, but let's get into it. Somebody taught me esoteric a number of years ago, but that's all right. It's a good word. But in a soft magnetic composite, we don't sinter. You say, well, how does that work? Well, you actually compact it, and then the powder is produced in such a way that it has this unique coating that effectively insulates each of the particles from each other. Not only does it give us this insulation, but it also gives us a level of strength that can be used in certain applications. And you say, okay, why is that important? Well, in AC machines, which represent 90+% or more of the total magnetics market, everything is, an AC device. And all AC means is that you vary the cycles. It's, coming out of the wall at 60 hertz. Some other machines it can be higher. And so now if you have this opportunity to say, hey, I can suddenly introduce powder into an AC machine, now it expands the horizon just beyond what we're doing in the car business, but now we can get into the household business, refrigerators, freezers, air conditioners. Right in front of us, this is a great part that you're producing right now, which is a motor that's ultimately used in a heating, air conditioning type application to circulate the air. And you might say, well, aren't the squirrel cage motors and things of that sort? Yeah, but people there are also interested in, how much performance, how much energy can I save over the cost of a motor?
Right. Yes.
And then you look at, the intermediate assembly and then the final assembly, and now all of a sudden you say, wow, that's really a clever device. And so you might ask yourself, well, what's the big deal? Well, I think the big deal is the fact that the purchase price of a motor, there's some estimates that it totally represents maybe 1-2% of the total cost of a motor over its lifetime. So if we can improve that performance, maybe spending a little more up front saves us as we go down the road. So it does two things. PM is obviously a green technology. We use the material wisely and we put it into the shape we want. But also it could be good for our environment in that we use less energy, less demand for electrical power as we go forward as well.
So a part like this is competing with the lamination steels.
Yes.
And so how does it compete then? You already alluded to the fact that, there may be some additional cost comparing this specifically to the lamination steel. So how does this compare then? Or how does the performance of this compare to a lamination steel?
Well, this is a very unique part, and it's a totally different shape than what you would consider with laminations. Can I reach around to get the part?
Of course.
Maybe this is a good. In one sense, if you think about conventional laminations, and we just so happen to have, a motor here. For those of you who are interested, this came out of my microwave that I happened to blow up one afternoon. But if you think about laminations, they're individual sheets of steel that are sort of stacked together. So I don't know how well that shows, but you can see the laminations in there. And so it's made of a series of stampings and then it's put together. Well, if you think about what we do now with SMCs, you put the powder in the die, if you will, in the mold, you compact it, and now you come up with this particular net shape. In one sense, comparing this to this is sort of apples versus oranges. This is called the so-called radial flux motor, where all the magnetic flux is generated radially. This is axially, so this goes up and down. So if you think about what SMCs can do is, if we were to try and make this particular component from a lamination perspective, it's going to be extremely difficult. You're going to be throwing a lot of material away, and you're also going to have other problems on the performance side. So what I think SMCs allow us to do is we can make the shape as is, very economically, and little to zero waste at that particular point in time. So it's a different concept in motors, and I think the performance side, people are saying, this works since Edison. Call it the late 1890s, and so that was what Edison came up with. Well, maybe it's time we moved a little forward from Edison and moved into the new century and said, what can we now do to take and improve the motor design? And I think SMCs offers us that opportunity, as we talked about before, from not only shape making, but maybe ultimate performance and ultimate cost savings for the end user as well.
So clearly shape making provides a benefit. It kind of frees the designer up, if you will, to be able to think in terms of optimizing their design. They're not limited per se to maybe the limitations of the lamination process.
Right.
And then of course the other side you mentioned is performance. So clearly we hear a lot of that today also in terms of increasing energy efficiency and so on and so forth. How can this help a designer improve the efficiency of their motor?
And I think a
Or,
lot
or
of...
what type of improvements might they expect?
Sure. If you think about some of the early motor designs, what people used to do is say, if I can plug it into the wall and the motor works, that's great. And that's what the thought process was. Now, with the advance in electronics, and to say, it's well known that if I increase the frequency of the device, I get better performance. Better performance means not only higher speeds, higher torque, but also lower energy consumption. So I think what SMC gives us that opportunity to go both ways. I mean, you have shape making, and now the ability with relatively inexpensive electronics, yes, maybe a bit more expensive, but like we talked before. All right, so I paid $1 more for this, but it saved me $100 over the life of the motor. Is that not a fair trade-off?
Right.
Yes, SMCs are a bit more expensive, but unfortunately, you don't get everything for free in this world. Sometimes you have to pay for it. And so, what was the old commercial, pay me now or pay me later? So in this case, it's, we'll pay a little more now, and we'll see more as a savings as we go later in the process. So does that help a little bit?
Yeah, I was going to say, I was even going to even a little bit deeper on that in terms of what specific types of characteristics might a designer be looking to improve through using SMC materials.
One would be heat. Okay. If you've ever grabbed the motor while it's running, it'll burn you. They're designed to run typically at about 140 to 150 degrees Fahrenheit. And so that's warm. And that heat isn't coming just because because it's losses.
Right.
It's because that's some of the electrical energy going in is being converted to heat. If we can minimize that and have it done that runs cooler, you have two advantages. Number one, less of the electrical energy is going into heat. And two, suddenly I don't need a fan on the end of that motor to keep it cool. So I can have this device that sits there and say, instead of running at 150 degrees, maybe this runs at 100 degrees without a fan. So now I have two savings. I have savings in less heat generation and less energy being required to spin a fan to keep the motor cool. So I think it's interesting. And at the early onset of SMCs, one of the big stumbling blocks was getting the electronics cheap enough. They far outpaced some of the other technologies in making that much more affordable. And so the electronics being so much less costly now, the difference in total upfront cost is becoming less and less.
Well, Fran, we asked this question on structural components. We asked this on sintered soft magnetics. We've got to ask the same question now for soft magnetic composites. What's the future look like for soft magnetic composite materials?
Somehow I thought you were going to ask me what was next. and that's exciting. And I think that if you think about where we are right now, when we say with an SMC that we press it, we don't sinter it. We go through a low temperature thermal cycle at around 1,000 degrees Fahrenheit. I'm a mastodon. I don't think in centigrade, so my training was in Fahrenheit. But one of the disadvantages to doing that is when you actually compact this powder into the shape, you introduce cold work into the iron. And we all know that if you cold work a magnetic part, you actually degrade its performance. So one of the things that has always been a challenge with the industry, and people have addressed it to some lesser degrees than others, then is to say, how can we get that temperature up so that we eliminate some of those ill effects of the compaction process? Compaction in that case is both good and bad. It's good and it gives us a shape. It's bad that now it has done some magnetic damage, if you will, to the part. So one of the things that has always been a challenge in the industry has been to say, how can we raise that, what we call the curing temperature, above, we found maybe 12, 13, 1400 degrees is a perfect temperature now to eliminate that cold working effect. The Japanese had an approach many years ago that was they actually took the iron powder and coated it with magnesia and compacted it, and then they could cure it. it was very expensive. And then you also had the ill effects of the magnesia sitting there. So I think, one of the things that we've been doing is we said, how can we take a basic iron powder and through some novel processing and novel techniques of coating that iron powder, get it so that now we can raise that curing temperature to 1400. And some of the early results that we've done are extremely promising. We've done some testing and we've got some reports right now that suggest, we can do that. And we can maintain that inner particle isolation and still give us the structural integrity that we're looking. So it's a fine line that we're trying to walk. And
let me just ask then, what does that mean to the customer?
What's that mean to the customer?
How does, again, from a performance standpoint, what becomes the benefit of something like that?
This goes back to, when SMCs were, as they were evolving, people would say, if you had an application at relatively low frequency, stay with the lamination approach. Because that cold working effect actually degraded some of the magnetic performance. If in fact now we can say we've taken away that one step of drop off in performance, so now this actually shifts some of the performance criteria where maybe now a motor like this becomes within the realm of possibility of doing. And so I think that, so from a performance standpoint, if we talk about it, we improve not only the permeability response, which is how quickly it responds to current, but we also decrease how much heat it's generating as well. This generates very little heat, but what if you can cut that back another 30%? What does that mean to your design?
Right.
What does that mean now also to your overall cost in terms of operational cost of that motor simultaneously? So if right now we're at an advantage of, let's say, 20% in that, and what if we can give you 30%, 35%?
Right.
Now does it become a much more widely accepted type of a product, and people are very willing now to say, hey, that really does work for me. Can we sign this up?
Right. Is there an optimum frequency for the use of SMCs in the current SMCs?
Yes.
Is there an optimal frequency that we could use the SMC material?
Yes, there is. And well, this happens to run, as you know, at pretty much 60 hertz line frequency, but it's a variable speed. And that optimal frequency will actually depend on what it's competing against. So this particular motor probably uses a relatively inexpensive lamination grade, an M50 type, which means it has 5 watts per pound core loss. All right, I got geeky on you, I apologize. But having said that, it's low grade. So if we're going to do an SMC comparison to this, if your operational frequency is 150 hertz and above, we're better. We're going to generate less heat.
Okay.
If you're taking some of the real high class, silicon lamination steels, that crossover frequency where SMCs become more efficient maybe shifts to 400 or 500 hertz.
Okay.
So if we think about it in that sense, just to make a blanket statement, say it's always better here or it's always better, it really depends on what we're competing against. That old boss used to say, you don't use a sledgehammer to drive a tack. You take a point of saying whatever the application is,
right,
this is what we're going to design to fit and what are going to compete against.
Right. And so some of the materials that you're working on right now, does that change that optimal frequency? Does that change that line of thinking a little bit?
I think it changes it dramatically. I think it truly is a game changer.
In what way?
Well, suddenly, we used to say, 200 hertz compared to this. Maybe suddenly that now is 60 hertz. You can plug it into the wall and it would work. Maybe in terms of some of the silicon steels, instead of having to be 400, maybe that's 150 or 200. So now what I think we offer is we offer this ability to not only have better shape making, but enhance performance simultaneously. So if a designer looks at it from the total perspective of not just one aspect, but shape, efficiency, performance, I think it becomes a more complete package in terms of what we can offer and what can be utilized,
Yes.
in the motor business.
Yeah. Very good point. So I want to thank you all for tuning in and checking out our little video sessions here on LinkedIn. We want to try to put these out on a regular basis. Again, what we're trying to do is give everybody a little bit of a sense of what powder metal is, and as Fran mentioned, talking about what are we doing to try to bring powder metal to the 21st century. So with that, look forward to seeing you in the future, and follow me on LinkedIn for more information.